and saying that all again for the recording because I forgot to turn it on. So tonight we will be having 2 presentations. I will be starting the opener with the last 2 constellations that are on our list, Octans and Pavo, and then we will have done all 88 of the modern constellations. And after that, we will be switching over to Doug, who will be giving the main topic on lunar evolution. And with that, now that I get so if I can get a confirmation that you all can see my screen and are seeing a PowerPoint slide.
Yeah.
Give me 1 second here. So Octans and Pavo, as I mentioned just 30 seconds ago, they are the last 2 constellations that we haven't gone over, and they not much really of interest in them, even for southern observers. So Octans is somewhere up in the middle rank in terms of constellation size. It's rank 50 of 88 in terms of angular area. It was one of 14 constellations that Nicholas Lacaille cataloged during his very long expedition to the Cape of Good Hope in the mid-1700s. He also cataloged all the constellations that he officially cataloged bear the names of scientific tools of the Renaissance and Reformation periods, such as the telescope, the octants, which is what the octant, excuse me, which is what the octants is named after. There's horologium and a couple of others, which we've gone over in the past. So his name is familiar for those that have seen some of these other presentations for southern constellations. It is, as I mentioned, it's named after the octant, which is a navigational instrument, which was very important in order for ships of this era in order to safely navigate the Atlantic and Pacific Oceans. It is the southernmost constellation. It occupies the space immediately around the South Celestial Pole, occupying much like the Little Dipper does here in the Northern Hemisphere. And of that characteristic, it shares that there's really nothing interesting deep sky-wise in this constellation that are accessible to amateur telescopes. There's because it's where it is on the celestial sphere. There's no open clusters. There's no globular clusters, and every galaxy in it is magnitude 12 or higher. So you'll need like a 14-inch telescope to make really anything out. A little quick star chart trying to showing its position. So over here to the, do I have a laser pointer? There we go. So over here we have Palvo, Indus, Tucana, Chameleon, and some others that we've gone over here in the past. So, and obviously right here is the South Celestial Pole. Kind of a brief overview list. We will talk about new octans, beta octans, and NGC 1798 briefly with this. Most other things, there's really just not much interesting. A couple of interesting variables, but nothing too spectacular. So new octans is a little bit of an interesting one. It is the brightest constellation, brightest star in the constellation, but interesting doesn't even have the alpha or beta Bayer designation, which is just alpha, beta, gamma designation that was given by Johann Bayer to most of the stars in the sky. And most times the brightest star in the constellation is cataloged as the alpha constellation name. So having it start off at new, bit of a curiosity as to why that happened, and I couldn't find much on why that occurred. The star is relatively faint. well, it's still naked eye visible, but it's just barely in there at around mag 3.73. It is 63 light years away, so relatively close for stars, well within our local cluster neighborhood. It's about 17 times brighter than the sun and is slightly over 1.6 times more massive. It fits in the spectral class K13, which the 3 meaning that it is entering into the giant phase. So this is a star that has moved off of the main sequence. It's approaching the end of its life here in a good while, and the K indicating its color spectrum. So it is, excuse me, it's more towards the orange color spectrum. I just got a, can anyone hear me just fine? I just had an internet warning.
Yeah.
Okay, making sure. Get your internet's unstable. So being what it is the brightest star, but there's no planets that have been observed around it. And there's no other astronomical uses or scientific curiosity. So it's kind of a really boring star for being the brightest one in the constellation. Kind of pointing out its position on the star charts here. So we have it's fitting one of the corners of the octant, moving closer towards Indus, which is interesting. And for our good friend, the HR diagram, saying over here that the star is well off the main sequence, which is this curve over here on the left, and moving up in towards the giant and supergiant phases. So Beta Octans is the second brightest star. It fits at around magnitude 4.1. It's also somewhat in our nearby neighborhood at 150 light years away. It is significantly brighter, a good chunk brighter than the sun, at around clocking in around 42 sols, and about 2.5 times more massive. It fits in the spectral class A94, which is in the subgiant category, with A denoting it's kind of more towards the whitish, it's a bluish white hue in terms of color. So still chugging on along. Still probably has a good amount of fuel to keep burning on for, I think A's have a couple 100 billion years more. It's interesting is that it is also an astrometric binary. We haven't been able to observe the orbiting companion directly yet, though. So it's really has just an inferred presence at this point. We don't know much about it. Again, our good friend, some star charts pointing out where it is, with Beta taking up the lower corner here, pushing more towards the constellation Hydrus. And as we can see, it is fitting pretty much here along the A main sequence branch. So it is in the main sequence, but it's mostly moving up and towards the subgiants, as I had mentioned. So it may actually be going, now that I look at this again, this may actually be going into a transition phase where it's in the process of moving off the main sequence and transitioning into the subgiant or giant phase in its life cycle. I didn't catch that the first time. And lastly, for octants with notable deep sky objects is NGC 7D98. It is a double barred spiral galaxy with a very unusual shape. With, as we can see in the picture on the right, it has two rings of very active star formation around a very devoid, very inert galactic core. All the blue in the image is very large amounts of active star formation. And so the double ringing is certainly an interesting aspect to go look at if you ever find yourself in the southern hemisphere. It is coming in at like magnitude 11.3. So you will need, I would probably say, at least a 10-inch telescope to see significant or good details on it. It is slightly larger than the Milky Way, about 50,000 light years more. The Milky Way fitting at around 100,000 light years compared to 7D98 to 150,000 light years. But it is a good chunk further away than most galaxies that we typically observe here in the northern hemisphere. About most galaxies, for example, most of the Virgo cluster objects in the Messier list, as well as some of the Leo cluster and Coma cluster objects, typically fit between the 30 and 50,000, not 30 and 50 million light year range. So this one is a good, about double that distance. So it's a little bit more unusual. It was first cataloged by our good friend William Herschel, who cataloged many of the NGC objects in 1835. And as I mentioned, the double rings on the outside, very indicative of a high radius star formation. There wasn't anything suggesting if this burst of star formation was triggered by a passing galactic neighbor, which we can kind of see one down here in the left-hand side of the image. I wasn't able to see anything that may have hinted about what caused this unusual double ring structure within the galaxy. So definitely something to go take a look at if we ever get down there. This is a rough simulation showing what the galaxy would look like in a telescope. This was done with simulating my 8-inch Schmidt-Cassegrain using a 10mm eyepiece. So it is quite small for your field of view, even at an 8-inch aperture. Kind of positioning off it's over off of New Octans, moving towards Indus. So might be somewhat more easier to find. And that kind of wraps up the general gist of Octans. As I said, there's not a lot to it. It's kind of in this boring part of the night sky, like a lot of celestial pole objects. Any questions before we move on to Pavo? Okay. So Palvo is the last of the constellations that we have remaining on our list. It is right in the middle in terms of angular size. It is 44 of 88 in terms of rank. It is Latin for the Peacock, and it was first observed by Dirksen Kaiser and Frederick Hauptmann in the almost in the 1600s, but it wasn't actually officially cataloged until our good friend Petrus Planicus, who we've seen work with some other constellations in the past, and Jodocus Hodonis, I butcher that name horribly, actually included it, and I think they sent it to, his name escapes me, the author of the Uranometria. If someone can chime in with reminding me of the author of that catalog's name, I would appreciate it. And that's where it first came into modern attention. Of note, it also lying significantly off the galactic plane. There are no open clusters in it, but there is one globular cluster. Excuse me one second. And two Caldwell objects. And actually, one of the Caldwell objects is the globular cluster, so that's a slight error on my part. And then a slattering of the typical NGC catalog galaxies that we normally see. A slight historical twist is that the Bayer designations for Pavo were not actually issued by Johann Bayer, but they were instead assigned by Nicholas Kai, who so that kind of was kind of like, that's odd. So I'm not quite sure why Bayer just decided to skip over Pavo when he was giving his designations. Despite being a southern constellation, this one does have a little bit of a myth behind it, which is unusual for it being so far south. It is actually associated with the shipbuilder Argos, excuse me. And it was, the story goes is that Argos, who was builder of the ship that Jason and the Argonauts sailed on, was turned into a peacock by the goddess Juno and placed along the ship in the night sky. So There were some potential references that the Greeks may have somehow been aware of this constellation, even though it is fairly far south. And I have a chat notification. Johann Bayer. Okay, thank you, Peter. Yeah. So Johann Bayer was also the author of the Uranometria. So thank you for pointing that out to me. Where were we? Myth. So it is a little bit weird considering just how far south this is. That it does have a little bit of a trace back to the Greek mythology. Where was I was thinking something else. Oh, excuse me. So Palvo is kind of down here. I'm not quite sure how they got the Peacock out of this. I kind of maybe potentially see this portion over here on the left being the tail, and then this being the Peacock's body and its beak coming up here off to the front. I mean, and its legs. I mean, I could kind of maybe see that. Still an interesting choice. A brief overview of list of, excuse me one second, of interesting things that can be found. We'll talk about Peacock and Lambda Palvo of the two stars in this list. And for deep sky objects, we'll be talking about NGC 6752, which is the only globular visible in this constellation, and the galaxy NGC 6744. Both of these two deep sky objects are part of the Caldwell catalog. So if you do find yourself a deep sky and maybe a photography person, these are good photography targets if you ever get down that south. So Alpha Pavonis, also given the common name the Peacock, is the brightest star in the constellation. It is about 180 light years away, and with an apparent magnitude of about 2 and a significantly high luminosity. It is about 2,200 sols and a solar mass of about 6 times more massive than the sun, fitting itself into the B-class stars, which are very hot, very massive stars, with stars sitting on the main sequence too, but designated by the V as part of the spectral class. So this is actually also a fairly young star, since Bs typically have a maximum lifespan of about 50 to 100 billion years. So this is, and the fact that it's still on the main sequence star says it is pretty young and just churning right along. It interestingly has 3 visual companions. Two of the companions fit around in the 9th magnitude, and the third is in the 12th magnitude range, with the maximum separation between all 4 components sitting at around 4 arc minutes. On top of that, the 2 9th magnitude stars are themselves a binary system. So this is both a visual, not technically trinary system, but it also has a binary component to that, which was actually kind of like one of those, I don't think we've seen that before in a lot of the stars we talked about with respect to the constellations. Fittingly for its name, it was actually given by the British Royal Air Force, according to Wikipedia, who in their quote said they insisted that all bright stars must have a name. So here we are talking about the star named Peacock. We can thank the British for that. Our good friend, the HR diagram showing where we are, we're way up here towards the top of the main sequence curve with this star. And it is sitting almost right here on the border between, almost in the constellation Telescopium and into Indus. So it's kind of there on the border, which is a very good distance away from basically anything else within the constellation that might be of interest in terms of navigational aids when you're trying to find things to go look at. The second star we'll talk about It was one of the only pretty variables that I was able to find that was worth mentioning, and I think I left the slide incomplete, and I regret that now. It is the seventh brightest star of the constellation, with a distance of about 14,000 light years. So in terms of stars, I think it's one of the farthest stars that's in the night sky that we can see unaided. I think Deneb is maybe slightly farther away at 1,600 light years. I do know that there is we start getting really spotty. So it definitely on the outer range of things within our nearby neighborhood, our nearby stellar neighborhood. It is cutting it close in terms of the visual range, coming in at that being a variable star. It has a range fluctuation of about magnitude 3.4 to magnitude 4.2. I couldn't find any numbers on the actual period and brightness in terms of how long it takes to fluctuate between its upper and lower intensities. But it is kind of a unique in that it is what was classified as a Cassiopeia variable star. And I ran out of time in terms of researching this particular object. Doug, I know you do a little bit more with variable star observing with the AAV. So have you heard of this subtype before? You can chime in on what this is.
I've heard of it, but I don't know anything about it. Most of my observations have been with mirrors.
If anybody else might have a little bit of insight into this variable star type, feel free to chime up after I finish this slide. It is also in the spectral class B. It is another main sequence star fitting in the spectral class B2. So this like Alpha Pavonis should be a relatively young star with a little bit shorter lifespan. A significantly shorter lifespan if this HR diagram is to be believed. So Alpha Pavonis came down a little bit farther south. And so with the way this star is turning out its brightness, it should be a much shorter lived star compared to Alpha Pavonis. Excuse me. And sitting kind of off over here towards the center of the constellation, where you can find it again. A lot of competing stars with similar brightnesses for it if the star charts are to be believed. So definitely one of those ones that may be a challenge to find. Moving on to deep sky objects. The first object of the two being Caldwell 101, also cataloged as NGC 6744. This is quite an interesting face-on barred spiral galaxy. It may be a little bit difficult to see, but I will try to point this out. So the bar is coming up here off the left hand and the right hand sides. And there's also down here what was pointed out was a companion dwarf galaxy to 6744 called 6744A, which is one of those things we don't see often in terms of unless the galaxy has been fairly close to for images that we can access anyway with our own equipment, is finding a dwarf galaxy like that. So it is a relatively close spiral galaxy, sitting at around 33 million light years away. Interestingly, it is part of the Virgo supercluster of galaxies, despite being so far past. Normally, most people associate the Virgo cluster and the Virgo supercluster as being, this more object, but it's actually a much more spread out cluster of galaxies that extends a good chunk of the sky. And so despite being, almost on the opposite side of the sky from where the Virgo cluster and the Virgo supercluster that we're normally familiar with is, it is still part of that group and is moving along with them gravitationally. It was originally cataloged in 1826 by James Dunlop before being included by William Herschel excuse me, in his NGC catalog in the mid 1800s. This is another IP simulation. So this galaxy has a fair size to it. This is, again, a 2008 inch Schmidt Cassegrain with a 10mm eyepiece. So this is, I think in angular size is roughly the same as the Messier 83 or Messier 101 for those that have observed those two objects. This is an object in similar angular size. So fairly bright core, some really good diffuse face-on features. Definitely a good object to go look at. Unfortunately, you know, we're kind of out of luck. And it is sitting off just off to the lower left here of Lambda Pavonis. So definitely one of those. Hopefully a little bit easier to find with that navigational aid. The last object is NGC 6752, also known as COD 193. It has been given the informal name of the Great Peacock Globular. Of the globular clusters in the night sky, it is actually the fourth brightest. The three more brighter ones are Omega Centauri, 47 Tucana, and Messier 22. Those three globulars are the only ones that are actually brighter than that. It sits just inside of the visual range for us, so it is technically one of the considered a naked eye globular cluster, sitting at magnitude 5.4. Although its size is such that you would need binoculars to see it. It is somewhat close for a globular, sitting at around 13,000 light years. Most globular clusters are sitting that we've talked about in the past are typically in 26,000 light years plus in terms of distance. But its mass is significantly on the low side for a globular cluster. Most globular clusters typically have up to 100,000, have a baseline mass of about 100,000 sols. This one is sitting at around slightly shy of 10,000. So it is a very
10
to the 5th.
You've got 1.4 times 10 to the 5th.
Yeah. So it's about,
well, that
about
would be
14 to 15,000 sols.
140,000.
No. 10 to the 6th. 10 to the 6th.
5th.
My math is, nope, you're right. My math is off. I can't think. I'm 10 to the 6th is million. I'm silly. Thank you for my math errors. I'm just ready to be done with school for the semester, so I'm excited with that. Retracting that statement, it's kind of in the middle range then for globular cluster masses. There was also a revised mass estimate that it's something like 2.4 times 10 to the 5th solar masses. So there's a little bit of fluctuation in there, and I'm not quite sure if the estimate that I picked was the more recent estimate in terms of its mass range. Again, ignore that last bullet point. That was an error on my part for not being able to learn how to multiply. Our last telescope simulation for this object, again with an 8-inch Schmidt Cassegrain and a 10mm eyepiece. So it is a very small and condensed globular. Excuse me. And you would like, and as you can see, this is most certainly at least a binocular object, if not a small refractor or better, to just be able to resolve some of its details. And
that's a nice looking globular.
A what?
That's a nice looking globular.
Yeah, isn't it?
Like, what do you use for your simulations?
I pull them off of Telescopius, which is what I also use when I'm, trying to size things up for, and doing some pre-session framing when I go out and do imaging. I use it a lot because it's pretty flexible in terms of like what you can input and when you're doing the frame simulations. And it's not like a specialty software that you have to download like Stellarium. It's just go to a web browser, put in numbers, done.
Right. Thanks.
And like Caldwell 101, which you talked about earlier, it is located more towards Lambda Pavonis over here in this region of space. And with that, some quick references. Most of the stuff you can, I frequently use these sites for various things. And any questions before we move on for the evening? Okay. Thank you very much. And with that, Doug, you should have screen share permissions. If we want to move on to you, jump right into Lunar Evolution.
Okay, it's not letting me do it. It's not letting me share screen. Oh, there we go. I got it.
Okay. I was about to be really confused because it's like that normally works.
Okay.
And I can see your screen, so you are good to go whenever.
All right. So this presentation, I'm going to talk about the evolution of the moon. It's what it's gone through during its life, its formation, and some other interesting things. I always do a little bit of comedy. I like this one. You can't look at the Milky Way because you're lactose intolerant. I like that one. Okay, so when you look at the moon, even through naked eye and binoculars, you see various different topographical features, terrain. So, you know, how did it form? What's it made of? And it's not made of cheese. How did the different terrain form and so on. And then I'm also going to talk about, well, how did we learn the information that we know about the moon, which a lot of that came from the rock samples that came back from the Apollo missions. And then we'll also talk about what's going to happen to the moon in the future. Oh, I got a phone here. Sorry, folks. Another thing you notice if you look at the moon, both the near side and the far side, is the first thing that sticks out as soon as you look at the near side and the far side, side by side like this, is that on the near side, you have all these dark areas, the lunar areas, the seas, if you like. And on the far side, there's basically none. And we're going to talk about that too, and try to explain why we see that large difference between the near side and the far side. There's been a number of different theories that have been proposed over the years as to how the moon formed. Most of the theories just were not viable. They had various problems that didn't match with observations. And it eventually boiled down to there were three basic theories that dominated the literature for centuries until we were able to bring back samples and we were able to do complex simulations on computers. And we were finally able to narrow it down to basically one theory. But just for fun, we're going to take a look at the three basic theories. And there's one that's called the capture theory, and there's another one called the fission theory, and then there's the third theory is called the collision theory. The capture theory is exactly what it sounds like. Early on in the beginning of the solar system, the moon was formed somewhere else in the solar system. it passed by the Earth, and as it approached the Earth, it got captured by the Earth's gravitational field. This theory was first proposed formally by an astronomer named Thomas Jefferson Jackson in 1909. The theory is not accepted anymore for a variety of reasons. It would have been very unlikely for the moon to get captured by the Earth. The Earth is so much is large, but not large to capture an object moon, but it could capture something the size of the moon, but the Earth just isn't big enough to really capture something. So it would be very unusual for the Earth to capture something like the moon. Also, there's a lot of similarities in the rock compositions between the Earth and the moon that you could not explain this way. And that's something that came out of the Apollo rock samples. It would be, you couldn't explain things like the oxygen isotopes and other things that are virtually identical between the Earth and the moon. That wouldn't happen if the moon formed somewhere else in the solar system. So that theory has been pretty much lost. The second theory that is actually still hanging around a little bit, but this is considered more or less an obsolete theory too, but it comes up occasionally. It's called the fission theory. And this is that early in the Earth's history, while it was still a molten blob, it had a lot of angular momentum spinning on its axis, and it just threw a piece of it off into space, just got separated by centrifugal force and got tossed out into orbit. And that would explain the similarity in the content between the Earth and the moon. And so this theory from time to time is still, people still write papers and try to revive this theory, but it's pretty much been rejected too, because there are things that don't make sense here. The angular momentum of the total system on the Earth and the moon doesn't work well with this theory. And there's other things that make this theory very questionable. But like I said, occasionally papers will get published where somebody tries to bring this theory back to life. So this one's not totally gone, but it's not the generally accepted theory. So theory number 3, and this is more or less the theory that is generally accepted today, is called the collision theory. And this was first, oh, I wanted to mention one other note. Back on this theory, interesting enough, the man who came up with this theory was a guy named George Darwin, son of Charles Darwin. So you had a botanist in the family and an astronomer too. So back to this theory now, the collision theory. This was raised at first by an astronomer named Reginald Daly in 1946, and it was raised as a direct challenge to the fission theory, which was at that time a fairly wide accepted theory. The collision theory actually explains a lot of the issues that the other two theories have problems with. And basically, it's exactly what it is. Something collided with the Earth early in the Earth's history. It was large. It was a big enough body that both the Earth and the object that hit the Earth were completely shattered. Most of the debris accreted into the Earth, but the debris cloud that was orbiting eventually accreted to form the moon. This theory has been refined, and with the advent of modern supercomputer simulations and analysis of the lunar samples now, this theory has been refined, and the latest version of this now is called the giant impact hypothesis. So the giant impact hypothesis now, and this is the current theory that is most widely accepted, is that about 100 million years after the formation of the solar system, so about 4.6 billion years ago, There were lots of objects floating around, many, 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 many more objects than you see in the solar system today. Something approximately the size of Mars, and they gave it a name. They call it Theia, collided with the Earth at a very oblique angle, almost a grazing collision. Both bodies were completely shattered. The larger debris field coalesced into the Earth. The smaller debris field coalesced into the Moon. The coalescing process was probably very fast. It could have been as short as 100 years. That's just based on their simulations. So this kind of goes through the timeline. So the impactor comes in, it hits the Earth. About 4 minutes after the Earth, things are breaking up. The debris gets thrown off into space because it's a grazing angle like that, so it gets tossed off into space. The Earth is shattered. The Earth reaccretes into a solid body down in the left-hand corner. Also, because of the grazing angle collision, the Earth gets knocked off its rotational axis, which could explain the 23-degree axial tilt that we have, because the Earth probably didn't form with a 23-degree tilt. The Earth probably formed more or less rotating in the same plane as it orbited the sun. This is also the theory they use for why Uranus is knocked on its side. It got hit by something. The Earth reformed, and then the Moon coalesced from the debris, and that's the system you see today. So like I said, this is this giant impact hypothesis. This is what we tend to accept as the current idea for how the Moon formed. Some of the evidence that they use to back this up is that the Earth's spin on its axis and the Moon's orbit have similar orientations in terms of their planes of rotation and the axis that they rotate about. If you look at the total angular momentum of the Earth and the Moon, it's very high. It's a lot higher than you would normally expect if the planets just formed out of coalescing together, or if the fission theory doesn't produce enough angular momentum either. So this produces a lot of angular momentum. The Earth rotates very fast, 24 hours. And so there's a lot of angular momentum in the system. Samples from the Moon, from the Apollo missions, basically have shown that the Moon was once very molten, perhaps all the way to its core. And that wouldn't normally happen either in a normal planet formation theory, but something like a giant impact where the two bodies are completely broken up and destroyed and then reaccrete would explain that kind of information that it is. The Moon doesn't seem to have much in terms of an iron core. It's got a considerably lower density than the Earth. Again, the other theories don't really explain that very well, but a large impactor type of collision would explain that very well, because the thought is that if a large object like the size of Mars were to hit the Earth, the core of that large object would probably penetrate all the way through down to the core of the Earth, and the two cores would get merged in the final body. And so all of the lighter stuff would get thrown off into space. And so the Moon would accrete out of a lot of lighter, less heavy stuff, which would explain why it's less dense than the Earth. The other thing they noticed from the samples that came back from the Moon is a lot of the lightweight volatile elements that you find in the Earth are not found in the Moon. And again, this theory explains that, because a lot of those light elements would have been vaporized, and lost in the high energy event, and the moon's gravity being small is unable to recapture them as the Earth recaptured them with its gravity. So that would explain that. And then there's other things. The other thing that came out of the lunar rocks is there are isotope ratios of various isotopes of different rocks that are identical in the Earth and the moon samples. And that sort of implies that they both came from a common origin. They both came from the same debris field, if you like. The theory is not perfect. There are issues. There are alternate theories, obviously, but most of the alternate theories have more issues. And this is an area of active research even today. We're still learning things. We still don't know all the answers. Just to set do a setup before we go farther. So after the Earth Moon finally formed as a system, things were a whole lot different than they are today. For example, the Earth's day was much shorter than it is today, perhaps as short as 6 hours. The lunar orbit distance was much, much smaller. It might have just been outside the Roche limit, and the lunar orbit period could have been on the order of a week. It was rotating around the Earth in a very short amount of time. This would have raised really, really large tides, both in the Earth and the moon. It would have caused large bulges in the crusts of the Earth and the moon. And we'll talk about that because that's actually going to have an effect on what we see when we look at the moon today.
Real quick, Doug, for those who aren't familiar, the Roche limit is a limit that says what's the smallest distance two bodies orbiting around each other can be before one of the bodies tears themselves apart from their mutual gravities.
Sorry, correct. I should have said that. And I don't know what the number is for the Roche limit for the Earth, but the moon was pretty close to it.
I think it's dependent on both bodies. I don't think it's dependent on
your
body. So
it does. But yeah, I don't exactly know what that number is. Over time, those tidal forces that I just talked about slowed the Earth down to where we now have a 24-hour day, and slowed the moon's orbital period down to where it's 28 days now, roughly where it takes to go around the Earth. But we'll talk about the tides later because that's an important thing. So, when you look at the timeline of a planet, you look at the timeline, the evolution of the Earth. The Earth went through various, what they call eras. You have the Jurassic era, all these different eras that the Earth went through during its history. Well, the planetary scientists have designated certain eras for the moon's history. The first one is called the Pre-Nectarian Era. It runs from about 4.6 billion years to 3.92 billion years. And then there's the Nectarian Era, which goes from 3.92 billion years to 3.85 billion years. There's what's called the Imbrian Era, which goes from 3.85 to 3.2 billion years, and it's divided into two different phases, what they call the early Imbrium and the late Imbrium. It's 3.85 to 3.8 for the early, and the late is 3.8 to 3.2 billion years. And then there's I love this name, Eratosthenean Era, runs from 3.2 billion years to 1.1 billion years. And then the era that the moon is currently in now started 1.1 billion years ago, and it's called the Copernican Era. And it runs it's right up to the current day. The moon is in the Copernican Era. So we're going to talk about these eras in chronological history. So the first one, like I said, is called the Pre-Nectarian Era. And this era starts with the formation of the moon. During this time, the Earth and the Moon were covered by global magma seas, which eventually cooled down and formed a crust. During this time, both the Earth and the Moon are still being heavily bombarded with debris that's left over from the solar system formation. The corresponding error in the Earth's history, there is an error that corresponds to this timeline, is called the Haitian Error, and it's named after Hades. And that's because basically you could say it's hell on earth at this time. I mean, this image, this picture probably is a good picture of what the Earth might have looked like with the moon there in the background during this time. Completely molten, lots of impacts, lots of meteorites coming down. Not a very nice place to be. Now on the Earth, there are no surviving rocks from the Haitian Era or the Pre-Nectarian Era. And basically all the early evidence of the Earth's early time scale has been completely erased by plate tectonics and evolution and everything else. There's nothing left from this early part of the Earth's history. But there are rocks on the moon that are more or less intact from this period of time. Samples that came back from the lunar highlands, Apollo 16 and Apollo 17, have been analyzed and have been determined to be from this era. They've got some rock samples that are that old. The rock samples are heavily churned and heavily brachiated, and brachiated means they've been shattered into small pieces and then put back together to form a larger rock. And that is mainly because even though the rocks themselves may have survived and not been melted, the total surface of the moon has been completely cratered over by impacts. And so a lot of the rock have been fractured and then got put back together in pieces. And so there's a lot of broken rocks on the moon, you might say. And this is where they got the information because of the crystallization, the way the rocks crystallized. They can tell that they crystallized out of a very large global magma ocean, if you like. I can tell that by looking at how the rocks crystallized. The Nectarian Era, which runs out to 3.85 billion years, is a period, again, we're still getting heavily bombarded. There's still a lot of leftover debris in the solar system. And this era starts with the formation of the Nectarian basis, Mare Nectaris, I think, and ends with the formation of Mare Imbrium. So they just picked two poles in two of the larger basins. And when this one formed, it starts, and when Mare Imbrium formed, it stops. This is a period during which, like I said, the Nectaris basin was formed, along with a lot of the other major basins were formed by large impact events. These are like very large asteroids that form these basins. Ejecta from the Nectaris basin forms some of the upper part of the cratered highlands in the lunar highlands. And one of the earlier questions you immediately ask, like I said, when you look at the pictures, is why are there no Mare on the far side? And we'll talk about that in a minute. But anyway, Apollo 15 landed right on one of the rims of Mare Imbrium and gathered back some very nice samples from the Nectarian Era. So we got rocks from here too. Now, as for why the near side looks so different than the far side, there are two mechanisms at work. One of them is fairly obvious, or at least I thought it was when they first explained it, is that during the earlier phase back here, during the pre-Nectarian and during the formation of the crust, the Earth took a lot longer to cool down than the moon did, because the moon is much smaller. So the Earth holds its heat longer. So the Earth remained molten for a much longer period of time than the Earth did. The moon formed its crust much quicker. But since the Earth did not form a crust right away as quickly as the moon did, it was still molten. It's radiating a lot of heat, okay? And the moon is orbiting very close. And so that tended to heat the near side of the moon, kept the near side of the moon quite warm, perhaps molten, for a lot longer than, let's say, the far side of the moon. So the crust on the near side formed later and therefore was thinner than the crust on the far side. Therefore, large impacts that penetrated the crust on the near side, and then the molten lava would come up through the cracks in the crust and fill in the seas. Those same size impacts striking the far side didn't penetrate all the way through the crust because the crust was thicker, okay? So that explains some of it. But still, when we look at the far side, we don't even see any large impact basins that are not filled with lava. So the second surprising one that I looked up and found, there's a lot of computer simulations on this. So early in the history of the Earth-Moon, the moon became tidally locked to the Earth. That is, the near side is always facing the Earth. It's rotating on its axis in the same amount of time it takes to orbit the Earth. That happened very early in the moon's history because of the huge tides. That would have happened very quickly. And the tides on the moon would have been enormous compared to the tides on the Earth. And so that immediately locked it into this tidally locked situation where the near side is always facing the Earth. Well, if you do a computer simulation and you randomly shoot asteroids at the Earth-Moon system, the asteroids that end up not hitting the Earth, that eventually do hit the moon, most of them will end up hitting the near side of the moon. They get deflected around the Earth right into the moon on the other side. Or they come in from a side angle and they get pulled into the moon instead of hitting the Earth, and they strike the near side of the moon. Surprisingly enough, almost nothing strikes the far side of the moon because the asteroids coming from that direction, unless they're on a direct collision course with the moon, if they even slightly miss the moon, the Earth just takes over and yanks them right into the Earth. And so they just don't hit the moon. They go by the moon and hit the Earth. And if the moon is on the other side of the orbit and the asteroid comes in, if it misses the Earth and goes around the Earth, it gets pulled right into the moon. So the moon acts as an attractor and acts as a pretty good shield for actually shielding the Earth from some of those impacts. So I found that's why a lot of like large impact basins, most of them are on the near side of the Earth. It's a pretty neat simulation too. I forgot to put the link up. I'll have to look it up again. And there were a couple papers written about it. I should have put them in here. I just didn't do that. I'm sorry. So you can look at the moon and you can find craters that are from the Nectarian age. And there's a really obvious one, Clavius. It's a huge crater down on the moon, and it's from the Nectarian age. And one of the things you notice when you look at it, like if you look at this image, is the rim is not very high. It's worn down. It does not have a sharp rim. It has no ray system. The crater itself, if you're just looking at its appearance, it's very heavily eroded. It's very beaten down. It's very flat. It's got numerous younger craters on its rim. The floor is cratered. It's just got a really, what you call a soft looking appearance when you look at it. I'm going to read some of the stuff that's on the chat real quick here. Let's start. Well, yeah. I don't know how long it would take to slide from the Earth to the moon. Sorry. Lunar rotisserie. I don't know what that is. Okay, let me continue. Okay, so now let's do the Imbrium era. And this era starts with the formation of mare Imbrium. And this is where the heavy bombardment starts to dissipate. So this era, or the early Imbrium, starts with the creation of the mare Imbrium basin, lasted about 50 million years. This is where the last large basins like Mare Crisis, Mare Tranquility, Serenity, Felicius, whatever, the last of the basins were formed during this early Imbrium period. And Apollo 14 brought back some samples from this era. And then the late Imbrium era, this is when the seas actually got filled in. This is where those large impact basins, the crust was shattered by the impact, and the lava, the salt, oozed up through the cracks in the crust and filled in these basins. And this probably occurred between 3.8 and 3.2 billion years ago. And Apollo 11, which landed in the Sea of Tranquility, brought back the samples from this era, and some of the Apollo 12 samples also came back from this era. And this is sort of what you might have seen had you been able to watch it. You have a large impactor, it comes in, it creates this large impact basin, which at first is not, if you look at picture D, the basin is just a large impact basin. It's not filled in with lava yet, but the crust is very shattered and broken. And then the lava starts welling up through the cracks and fills in the floor of the crater, and then starts, and eventually you have the other impact basins which get filled in the same way. And you get to picture H, which is what the moon looks like today. What is this one? The Eratosthenean era runs from about 3.2 to 1.1 billion years. Now, in this era, the moon is still getting hit with impactors, meteorites, and so forth, but not the very large impactors that we saw in the earlier eras. The period of what they call heavy bombardment has more or less stopped in the solar system. But what you notice when you look at these craters is, again, they may have sharp features, sharp rims, and other features, but they don't have rays, okay? They tend to be soft. Like I said, they tend to be worn down by what we call erosion, and they may be filled with ejecta from other impactors. So for example, if you look on this picture, okay, the crater in the upper left is an Eratosthenean crater. It doesn't have any rays, okay, but it's a fairly sharp looking crater. It has boulders in it. It doesn't look worn down yet. But then you compare it to the craters down on the bottom of the image, like this one, or this one. These are old craters, probably pre-Eratosthenean craters. They're very worn down, they're very soft, no features to them. This one may be an Eratosthenean crater because it's got some boulders in it and it's somewhat sharp, but they date craters by looking at these features like this. And so you've got some craters that are younger than others and some that are very old. In fact, this one, like I said here, is probably pre-Imbrium. This one really looks old. And finally, you have what's called the Copernican Era. Era started about 1.1 billion years ago and continues to the present day. And the main thing about this period of time is that any craters that were formed in this period of time still have ray systems. They figured out that ray systems, on average, take approximately 1 billion years to get completely wiped out by erosion. And erosion on the moon, when they use the word erosion, they're talking about the continuous bombardment of micrometeorites. The micrometeorites slowly wear down the features and soften everything. The boulders in these pictures, slowly the micrometeorites will pulverize them down to where they're not boulders anymore. They're just be piles of debris, lumps of dirt, or lumps of soil, if you like. And eventually the sharp features of the crater will get worn down to where it looks like one of these craters. And that just happens from the constant bombardment of micrometeorites. And they figured it takes about 1 billion years to destroy a ray system. So any crater you see that has rays was formed during what's called the Copernican Era. So obviously here's some examples. I mean, Tycho down here in the left, Copernicus, obviously the era is named after Copernicus. Here's another crater. I don't even know the name of that one. It's got a nice ray system. But that, you know, those are the new craters that you see. Apollo 12 landed right on one of the Copernicus rays. And so some of the samples that came back from Apollo 12 were from the Copernican era. So now where is the Earth and the Moon going to end up in the future? So the Earth is slowing down in its orbit, the length of the day is getting longer. And the moon is moving away from the Earth. And that's because of the tides. And like I said, the tides are very important to the evolution of the system. If you think of the tides as a couple of bulges, like my picture shows, that's a very primitive picture. So the moon raises tidal bulges. And we're not just talking about the water. It actually raises tidal bulges in the crust of the Earth. And because the Earth rotates in 24 hours and the moon takes 28 days to go around, the tidal bulges move faster than the moon does. They're always offset. They're always a little bit ahead, like my picture shows. It's a little bit ahead of the moon, okay? As a result of that, the tidal bulge that's closest to the moon is pulling the moon forward in its orbit, okay? And the tidal bulge that's on the other side of the Earth is trying to pull the moon back in its orbit. But the tidal bulge that's closest, because it's closest, the gravitational force, if you like, between the moon and that tidal bulge is a little bit stronger than the gravitational force between the moon and the tidal bulge on the far side. So the force is a little bit larger. So the net effect is the moon is speeding up in its orbit. It's getting pulled along at a faster speed. Well, when you have something like a moon orbiting the Earth and you increase the velocity, it moves outwards, it spirals out, okay? So the moon is spiraling away from the Earth, slowly, not much, but it is. At the same time, for every force, there's a counterforce in the opposite direction, Newton's law, whatever. The moon is pulling on those tidal bulges. And again, it's pulling on the closer bulge with a larger force than it's pulling on the bulge on the far side. It's actually pulling the Earth. It's pulling the Earth down, if you like. It's trying to slow the Earth down in its orbit, in its rotation, if you like. And that's why the Earth is slowing down. The day is getting longer. And this has been going on for billions of years, because remember, I told you at one time the Earth's day was probably as short as 6 hours. Because of the tides, it's now 24 hours. Eventually, the system's going to reach an equilibrium, and that's going to happen when the moon's orbital period precisely matches the Earth's rotation period. Or in other words, the moon will be in a geosynchronous orbit at that point. And then the Earth and the moon will have the same faces facing each other all the time. So the moon will never set on one side of the Earth, and you'll never see it if you're on the other side of the Earth. But we don't have to worry about that ever happening. It's going to take billions of years. In fact, the sun's going to burn out before we get to that point. Now, this is actually a simulation. I ran this simulation when I was in graduate school. This was a fun one to do, actually. Oh, and that's my last slide. Okay, so I'll take questions now.
Hey, Doug, it's Pete, just a comment, well, maybe a comment and a question. I mean, one thing, good presentation. I think a lot of times when we associate lava flows, we think volcanic activity. Of course, I don't think there was absolutely no volcanic activity on the moon whatsoever, and it was just primarily
that's not true, actually.
Go ahead.
There was volcanic activity on the moon early on.
Okay.
During the early days when the crust was still cooling and things were happening, there was lots of volcanic activity on the moon and the Earth, a lot more than what you see today. It wasn't caused by plate tectonics like it is on the Earth today. It was just caused by the fact that the crust was still forming, and every time early in the history, every time any kind of a meteorite would hit the crust, it would probably cause something enormous to happen in terms of volcanic activity. As the crust got thicker, the volcanic activity tended to die down.
But yet the main mechanism for the creation of the Maria on the Earth-facing side here again is primarily what you alluded to, not volcanic. It might have some contribution, but most of it was heating from the Earth and the heating from the impacts that occurred on that side.
Yes. Well, what happened is the primary mechanism for the formation of the Maria was you had the large asteroid impactors that were striking the near side of the Earth. And like I said, they weren't basically striking the far side at all. They were penetrating the crust all the way through to the molten interior. And they would leave the crust completely shattered in those impact basins. And the lava would ooze up, it would well up through those cracks. It would slowly work its way up through the cracks, taking millions of years, but would eventually work its way up through the cracks. And it would start by, it would start oozing out over the floor of those impact basins and start filling up the whole impact basin. It would take a long time. It was not just a whole lot of lava squirting up at one time. It was a very slow process. But because the crust was so badly shattered by those impacts, it found its way up through the cracks.
I would also expect
that's interesting. That answered my question before I put it, because I was wondering how deep did these lava flows come from? In other words, how, because of the impacts. So what you're telling me is basically it went, substantially into the crust to the core, basically. I mean, let's give it a figure of half of its radius going in. I would take it.
Now, remember, we're talking about three.
No, I get it.
The crust was a lot thinner than it is today, for example, but the crust was very shattered. I don't necessarily suggest that the asteroid would have penetrated all the way through to the lava underneath the crust, but it completely shattered the crust. It just cracked it really severely, and then the lava oozes up through the cracks. There's evidence of volcanism on the moon. You can look at some places where you can find lava domes and things like that, where there's evidence of volcanism on the moon, and it did occur early in the moon's history.
Okay.
Another potential source of volcanism would also come from tidal heating, like on Io. Given the moon's close proximity early on in its age, there would have been significant tidal friction.
Early on, there might have been a lot of weird things happening when it was real close like that.
But I think that even with the tidal heating, it would probably still have not been as significant as any molten activity caused by any of the strikes or other general goings on. It wouldn't have been a significant factor. I think.
Right.
Don't quote me on that.
This is still an area of active study too, but they learned a lot from the samples that came back from Palvo.
Questions? I'm just wondering how small a micrometeorite is.
Oh.
Yeah, I'm just wondering how they would compare to a meteorite here.
We're talking dust-sized particles, literally micrometeorites. Little itty bitty grain of sand or smaller type particles, but
Oh,
they're constantly raining down on the surface of the moon. They're raining down on the surface of the Earth, but we never see them because they don't penetrate the atmosphere. But on the moon, it's a constant bombardment, and it eventually pulverizes everything.
yeah, because they don't have much of an atmosphere, right?
Right, no atmosphere.
Nothing to slow them down.
Yeah.
And then, let's see, I'm just wondering, the moon doesn't have a molten core at all anymore, right?
I don't think so. I read papers, and some papers seem to think there is still some bit of a molten core, but most papers I read, they think that it's completely solid now all the way through to the core. It's completely cooled down to where it's just a solid rock.
Yeah, and I was just wondering, this isn't really about this exactly, but I wonder if all the planets were molten to begin with, do you think? And then they slowly, I mean, I guess they're accretions of stuff.
Yeah, the general theory on planetary formation in the accretion process, they start out as molten. And that's from the gravity. When you get a large enough body, the gravity is pulling the stuff in and the gravity is heating it up, and it becomes a molten ball and then cools down when the accretion process stops.
Cool. And I wish I could see a molten magma seas with tides, but not here.
The tides would have been humongous during that early phase, and they would have been molten tides that could have been hundreds of feet in height, really, really enormous tides.
All right, very cool. Thank you.
Oh, so my brother gave me this really neat moon lamp, and it actually has the topography on it of the moon. So you can look at it, and you can see the Maria on here, and on the near side. And when you turn it over to the back side, you can see that it. Well, I can't show it on here, but you can see that it doesn't have. They don't have any craters on the other side.
There's almost no Maria on the other side.
No, it's pretty smooth.
I mean, there's a hint of a couple impact basins on the far side. Get back to that. Sure. Okay, so this one here, this is the Russian crater that was spotted when the Soviets they were the first ones to send a spacecraft around to take pictures of the far side, and they named this basin there after a Russian. I don't know.
Yeah, I can see that.
Tchaikovsky or something like that, it's called. And that's a little impact basin. It's not a very big one. And it sort of looks like there might be impact basin down here, but it didn't get filled with lava. And so this may be a case of where the impactor didn't penetrate the crust far enough to allow the lava to come up. Okay. And so that could go along with that idea where I said the crust on the far side was thicker than the crust on the near side. And so the impactors on the near side penetrate a little more easily than they do on the far side, or shatter the crust a little bit more than they do on the far side. So this may be a case of where the impactor hit a part of the crust, but not quite enough to shatter it to allow the lava to flood up and fill in the basin. But other than that, there's basically no impact basins on the far side.
Well, what I always find fascinating with the moon too, when I've done my astronomy classes and learned about, is the phases, and seeing how the full moon always happens when the sun comes up, when the moon rises at sunset, and then how the new moon is when the moon sets with the sunset.
Mm-hmm.
And it's always that way, and even regardless of the season and everything.
Oh, yeah.
It's amazing how that
happens.
happens.
If you think about it, it has to be. The full moon is always going to be when it's directly on the other side of the Earth from the sun. It has to be 180 degrees around from the sun in order for the whole face of it to be illuminated. So it has to be that way.
Yeah.
Just like the new moon is always, yeah.
So then what happens during the eclipse? I know
during the eclipse
Sunday.
that's coming up on Sunday, the moon is going to pass through. If you think about it, the Earth now is between the sun and the moon during a full moon, okay? Well, the Earth is casting a shadow out into space, okay? And during an eclipse, the moon is passing through that shadow.
And it doesn't happen all the time because we're not on the same plane.
Right. The moon is not orbiting in the same plane the Earth is orbiting. There's only two across each other, which is roughly twice a year.
And then you were talking about how meteors, some of the meteors are kind of absorbed by the moon, and so sometimes the meteors come and they kind of slingshot around the Earth and hit the moon, and then sometimes the moon kind of slingshots them into the Earth. Is that?
So that was sort of a discussion on why there are so many large impact basins on the near side and you don't see any on the far side. And that's basically, if you run a computer simulation and you randomly shoot asteroids or meteors, if you like, into the Earth-Moon system, if you shoot an asteroid at the Earth-Moon system just randomly from different angles, if it doesn't hit the Earth, if it hits the moon, what you find is that it's usually hitting the moon on the near side, on the side that's facing the Earth, okay? If the moon was not tidally locked, like it is now, where the near side is always facing us and the far side is always facing away from us, then those impacts would be randomly distributed because the moon would be rotating and not always facing the Earth. But the fact that it's facing the Earth all the time, the asteroids are always coming in and getting bent by the Earth's gravity, and they're always coming in and they're hitting the moon on the side that's facing the Earth. And I'll have to look up that simulation. I lost it. I'll have to look it up and find it, and I'll send a link out to Connor when I find it. It's actually a pretty cool simulation to watch. But that was something I didn't think of. I mean, I knew about the fact that, or the theory that the near side crust was thinner than the far side crust because of the radiant heat from the early Earth kept it molten for a longer period of time. But I hadn't heard about the theory, the simulations that showed that the asteroids were always going to hit the near side of the Earth. That was new to me.
On the topic of eclipses and shadows, I did post a picture showing what the apparent shadow of various stellar objects would be if you were to put them on the Earth, such as how big, how would Venus's shadow compare if you could see Venus's shadow. Doug, as a reminder, can you send me this presentation? And I also, the archive copy I had of your astronomical onion presentation apparently got corrupted in the Google Drive. If you could resend me that one, because it shows up as zero, as a file of zeros of size 0, and it's, I don't know what happened to that.
I still have it, I'm sure.
Stephen's still here. He is not. He apparently left. I'll have to follow up with him. I do believe that Stephen Ferris will be doing the main topic next month. I think it's on the history of large telescopes. I would need to double check with him. But I also don't have anything else lined up for next month in terms of other content. So we finish all the constellations now. That kind of leaves it like, hey, start over or do something new. Because we don't actually have archive presentations for all the constellations, which might be a nice thing to have, but you know, taking another 4 years to finish up the 44 constellations that we don't have presentations for might be a little bit of a time kill. So if anybody has any suggestions for other content they would like to see next month, I will make my efforts to put something together. There any suggestions?
Well, somebody could do a presentation on any type of sky object that you find interesting, like globular clusters or open
I
clusters,
would,
or
we have main topics on some of those. I was thinking more along
Yeah.
going in with the astronomer spotlight, which I've floated around before, maybe starting out with
that
Hubble.
would work.
Okay, I'll think about that, and if I can come up, if I come up with something, I'll let you know. I still got my Man in the Universe thing. It's still on my list of things to do. It's not done yet, but I'll let you know when that one's ready, Connor.
Thanks, Doug.
And I can probably put together something for an astronomer of the month if you like. I'm sure I can pick somebody interesting.
Let's save that one for the July, Doug, for you for that, and I'll take next month for
Okay.
Yeah, you got some really good ones, Doug. You know, like when you did Tycho Brahe and all that.
Yeah.
So, so that's kind of the rough plan for next month. We'll see if work-life balance permits me to do that.
Okay.
I don't know, is it possible to do something about, say, when objects collide, what happens? Like the different possibilities, or is that worth a whole class?
That
Oh,
would be
like
interesting,
maybe
but it
when
would also be,
galaxies collide.
What?
Like when galaxies collide?
Or any collisions.
that would be
That
an
would be an
interesting one, but
interesting
I would need to it would probably be one that would be a longer term thing to put together. Just because I think that's one of those that needs a lot more visuals and videos with it. And so there would be a lot of hunting with that to like find accessible videos. There's certainly ones that exist, but I don't want to have a PhD to explain a PhD to explain a video.
And there's lots of really cool computer simulations for that.
Yeah, I bet.
Well, another topic, right? You know, they just have this stuff in the news now about the Event Horizon Telescope, and you know, and the Sagittarius A star. You know, and I was wondering, just might be a crazy, uninformed question, but they use the Event Horizon Telescope to focus on the black holes. But what if you tried to use it to get higher resolution on some other things in the sky?
It's mostly, so the Event Horizon
Yeah.
Telescope is largely a radio telescope.
Oh yeah, that's right.
So there's like, I know they also pointed the Event Horizon Telescope at the galaxy Sagittarius A, which did also produce some interesting images. It's one of those, it's a lot of power to focus on some things. So I think they're very selective with their targets and what they can do. And, you know, you need a lot of radio signal or a high radio energy object to pull things out. Or, you know, you have a whole bunch of other side effects you have to consider.
So something else I thought of, and this is just, I'm just going to put it out there for the rest of the people. I know we've discussed this before on and off, but like fundamental topics, real basic topics, because sometimes I think we get a little away from basic topics and we get into the more advanced stuff. And I want to, if there's fundamental topics that people might be interested in, like newbies who don't know anything about telescopes, and maybe I think we should keep a perspective there and occasionally give talks that somebody might want to see in terms of related to very fundamental stuff. So if anybody's got any ideas on that, I'm sure we'd be happy to take a look at those.
One thought is how about current and upcoming events in the sky? For example, we've got the morning planetary alignment. Maybe a talk about orbital dynamics and Einsteinian effects on Mercury's orbit and things of that.
Well,
that
Einstein's
nature.
effect on Mercury's orbit is a pretty advanced topic.
And of course, we have the big solar eclipse coming up in a couple of years.
Okay.
Maybe something
We have an archive presentation on solar eclipses, Thomas. If you would like me to send that to you, I can send that right now and throw it inside of the chat if you were interested.
You know something, Connor. The idea of having a quick little 5 or 10 minute spiel on upcoming events, like
Oh,
the
yeah.
close approach, we could throw something like that in as a regular little thing every month. Although they also do that in the general meeting, or they used to.
Oh, they only do it every quarter with Mary.
Well, yeah, but remember, I can't remember the name of the old guy.
They had a
Who's-
what's in the night sky where they
yeah.
talked about like the planets and what the planets were doing.
Yeah,
at certain
that
points.
I can't remember his name. He would get up every month and give a short
One with the
little
German
talk.
accent.
Yeah, he would give his little talk about the planets each month. I don't think he's
Yeah.
been doing that when we've been doing the Zoom meetings, right? I
Is he
haven't
still
seen him.
even alive?
I think so. Maybe not. But that might be something we could pick up. Do something like that, 5 minutes. Here's what's up. Here are
Yeah,
the
absolutely.
planets. Now I do that. I mean, I publish that
Yeah,
in
you
the
do
bulletin
it.
every month. Okay.
I think doing that would be
bulletin-
a good segue between when we're going between the opener topic and the main topic.
Okay.
Would be a good transition.
I put that information is going in the bulletin that everybody gets from David Rossiter. I put that what's up list thing in the bulletin that also has a section on where the planets are and which planets you could see in the morning. And which
Yeah, which
planets-
constellations you can see.
Yeah, that's all in the bulletin, but it might be a nice thing to put in the talk for 5 minutes or so. Because I don't put in anything special, like I don't say anything about the fact that there's 2 planets close together in the sky. I'm just telling you where the planets, it's an evening object or it's a late object, and some basic information about how to find them. So that might be useful.
I like that idea because sometimes I learn better, I remember better when somebody says it out loud than
Okay.
reading it, or I'll lose track of the bulletin.
Okay.
Another idea I had is maybe something about magnetism, just
About what?
magnetism in
Oh,
general.
magnetism.
Maybe.
Huh.
I don't know.
Okay.
I know different planets have different magnetic fields, and the moon
Oh,
doesn't have one, does it? I don't even know.
has one, but it's very small.
Yeah, a little bit.
Oh,
I don't know much about.
perhaps I'll talk about the magnetic fields of the planets.
Sounds like getting into physics.
That,
You don't have
I-
to, you don't have to get too much into physics to give a talk about magnetic fields.
Mm,
That has a lot to do with planetary formation. So that might be an interesting talk. So,
And Doug, one piece to add on to the, highlights in the sky for the month would be including such things. And this, granted, this involves a little bit of research, and I know it's out there in other sources, but comets that are showing up in the near term,
okay.
asteroids are going to become more visible, especially as far as some of the top 15 and where they may be lying. Not getting it real way into the weeds, but putting those kind of highlights in there would be kind of a nice add too.
Okay.
So
Keep that in mind.
some things for us to think about for next month. Thank you all for the good feedback. And with that, I'm going to stop the recording and I am going to